What kinds of pressure are you feeling right now? How do you usually handle them?
Do you feel any pressure right now?
No, I don't feel any pressure right now.
Pressure can sometimes feel overwhelming, like too much to handle, especially when expectations and challenges are high. But pressure isn't always bad. It pushes us to grow, adapt, and become stronger. Without it, we might not develop the resilience and determination needed to overcome difficulties. In the end, pressure helps shape us into stronger individuals. In chemistry, pressure is also very important, especially when studying gases. Along with temperature and volume, pressure affects how gas particles move and how much space they take up. Changes in one of these factors can affect the others. Understanding their relationships help us predict how gases behave in different situations. In this video, we'll explore the relationships among pressure, volume, and temperature using the main gas laws. We'll focus on Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. But before we dive into these laws, let's review the key quantities we'll be working with: temperature, volume, and pressure. Temperature is the average kinetic energy of the gas particles. The higher the temperature, the faster the particles move. When a gas is heated, its particles move faster and spread farther apart. This means the gas expands and takes up more space. Volume is the amount of space a substance occupies. According to the kinetic molecular theory, ideal gas molecules have very small volume compared to their container. These allow gases to be compressed or expanded. When a gas moves to a larger container, it quickly expands to fill the space. Gas particles move in the straight lines until they collide with each other or with the walls of the container. These collisions are elastic, meaning no energy is lost. When particles hit the walls, they exert a force per unit area, which we call pressure. Gas laws describe how gases behave based on pressure, volume, temperature, and the amount of particles. Some of the main laws include Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, Avogadro's law, and the ideal gas law. We can use the combined gas law to show the relationship among pressure, volume, and temperature of gas when the amount of gas is kept constant. The combined gas law shows that the ratio of pressure and volume to temperature remains constant for a given amount of gas. It states that the product of the initial pressure and initial volume divided by the initial temperature is equal to the product of the final pressure and final volume divided by the final temperature. Take note that the temperature should always be expressed in Kelvin, while pressure is commonly measured in atmospheres and the volume in liters. Using the equation of the combined gas laws, we can actually derive the formulas for other gas laws by keeping one variable constant. This shows that combined gas law summarizes the relationships among pressure, volume, and temperature in gases. For instance, if the temperature remains constant, the equation simplifies and we obtain Boyle's law, which describes the relationship between pressure and volume. If the pressure remains constant, the equation simplifies to Charles' law, which explains the relationship between temperature and volume. If the volume remains constant, the equation becomes the Gay-Lussac's law, which shows the relationship between pressure and temperature. For now, let's first focus on Boyle's law and understand how pressure and volume are related when temperature remains constant. Boyle's law states that at constant temperature, the pressure of a gas is inversely proportional to its volume. This means that when a volume increases, the pressure decreases, and when the volume decreases, the pressure increases. It is denoted by the equation P sub 1 V sub 1 is equal to P sub 2 V sub 2, where P sub 1 and V sub 1 represent the initial pressure and volume, and P sub 2 and V sub 2 represent the final pressure and volume. Let's try to apply this concept to a sample problem. A sample of gas occupies a volume of 0.35 liters under a pressure of 0.75 atmosphere. If the temperature remains constant, at what pressure will the gas be when the volume changes to 0.26 liters? This problem can be solved using the Boyle's law since the temperature is constant and only the pressure and volume change. First, identify the given values. The initial volume is 0.35 liters. The initial pressure is equal to 0.75 atmosphere. The final volume is 0.26 liters, and the final pressure is unknown. The formula is P sub 1 V sub 1 equals P sub 2 V sub 2. We need to solve for the final pressure, so we will derive the formula by dividing both sides of the equation by the final volume. Thus, the formula will be P sub 2 equals P sub 1 times V sub 1 divided by V sub 2. Substitute the values. P sub 2 is equal to 0.75 atmosphere times 0.35 liters divided by 0.26 liters. P sub 2 is equal to 1.01 atmosphere. Therefore, the final pressure is approximately 1.01 atmosphere. This shows that when the volume decreases, the pressure increases, which follows the Boyle's law. A scuba diver has a 2.5-liter air tank filled with compressed air at a pressure of 200 atmosphere. If the diver ascends to a depth where the pressure drops to 50 atmospheres, what will be the new volume of the air in the tank, assuming the tank temperature remains constant? Since the temperature is constant, this is still a Boyle's law problem. Let us identify the given values. The initial volume is 2.5 liters. The initial pressure is 200 atmospheres. The final pressure is 50 atmospheres, and we are looking for the final volume. We want to find the V sub 2. Starting from P sub 1 V sub 1 equals P sub 2 V sub 2. Divide both sides by P sub 2, which will result to V sub 2 equals P sub 1 V sub 1 over P sub 2. This is the formula that we will use to calculate the final volume when the temperature is constant. By substituting the values, we will come up with a new volume of the air tank, which is 10 liters. This means that as the diver ascends, the external pressure decreases. The gas expands. This behavior perfectly follows Boyle's law, showing that the pressure and volume are inversely proportional when temperature is constant. Now that we understand how pressure and volume are related, let's look at a real-life application. Have you ever wondered why airplane cabins are pressurized? As an airplane climbs to high altitudes, the outside pressure drops significantly. If the cabin were not pressurized, the air inside would be too thin for passengers to breathe comfortably, and the volume of gas in our bodies would expand in unsafe ways. By pressurizing the cabin, airlines maintain a safe and comfortable pressure similar to what we experience at lower altitudes. This is a perfect example of Boyle's law in action. As pressure decreases, gas tends to expand. The cabin pressure prevents this expansion from affecting passengers and ensures we can breathe normally at high altitude. Now that we have seen how pressure and volume are related when temperature is constant, let's explore what happens when pressure is constant instead. This brings us to Charles' law. Charles' law states that the volume of a gas is directly proportional to its absolute temperature as long as the pressure remains constant. In simple terms, when a gas is heated, it expands. When it cools, it contracts. A perfect real-life example is a hot air balloon. When the air inside the balloon is heated, the gas molecules move faster, spread apart, and the volume of an air increases. This makes the balloon less dense than the cooler air outside, allowing it to rise. Conversely, if the air inside cools, the balloon descends. In this experiment, the air inside the flask is being heated. According to Charles' law, as the temperature of the gas increases, its volume also increases. You can see the balloon inflating because the heated air inside is expanding. This simple demonstration shows how gases respond to changes in temperature. Just like in hot air balloon, heating the gas causes it to expand, and cooling it would cause it to contract. Charles' law helps us predict and understand this behavior in everyday life and in science experiments. Mathematically, Charles' law is expressed by the equation V sub 1 divided by T sub 1 is equal to V sub 2 divided by T sub 2. Here, V sub 1 and T sub 1 represent the initial volume and temperature, while V sub 2 and T sub 2 represent the final volume and temperature. It is important to remember that temperature must always be expressed in Kelvin when using gas law equations. Now that we understand the formula for Charles' law, let us apply these concepts to some sample problems to see how temperature changes affect the volume of a gas. A basketball has a volume of 7.5 liters when stored in a cool gym at 280 Kelvin. On a hot day, it is left outside and the temperature rises to 310 Kelvin. Assuming no leaks and constant pressure, what will be the new volume of the basketball? This problem follows Charles' law, which states that the volume of gas is directly proportional to its temperature when pressure is constant. Step 1 is to identify the given values. V sub 1 is equal to 7.5 liters. T sub 1 is equal to 280 Kelvin. T sub 2 is equal to 310 Kelvin. We are looking for the V sub 2. Let us derive the formula for V sub 2. V sub 1 over T sub 1 equals V sub 2 over T sub 2. Multiply both sides by T sub 2. We'll get V sub 2 equals V sub 1 times T sub 2 all over T sub 1. Let's substitute the values. V sub 2 is equal to 7.5 liters times 310 Kelvin all over 280 Kelvin. We'll get the final answer. V sub 2 is approximately 8.30 liters. Since the temperature is increased, the volume of the gas inside the basketball also increased, which follows Charles' law. Next, Ella visits Tagaytay, where the temperature is 20 degrees Celsius, and inflates a balloon to a volume of 1.5 liters. Later, she travels to Manila where the temperature rises to 35 degrees Celsius. Assuming the pressure remains constant, what will be the new volume of the balloon? This problem follows Charles' law, which states that volume of gas is directly proportional to its temperature when pressure is constant. Step 1 is to identify the given values. The initial volume is 1.5 liters. The initial temperature is 20 degrees Celsius. The final temperature is 35 degrees Celsius. Remember that gas law calculations require Kelvin. So let us convert the temperatures to Kelvin. For the initial temperature, 20 degrees Celsius plus 273.15 equals 293.15 Kelvin. The final temperature is 35 degrees Celsius plus 273.15 equals 308.15 Kelvin. The equation is V sub 1 over T sub 1 equals V sub 2 over T sub 2. Let's derive the formula for V sub 2. V sub 2 is equal to V sub 1 times T sub 2 over T sub 1. Substituting the values, we get V sub 2 equals 1.58 liters. For the final answer, the new volume of the balloon is approximately 1.58 liters. Since the temperature increased from Tagaytay to Manila, the volume of the gas inside the balloon increased slightly, which follows Charles' law. From this example, we can see that when temperature increases, the volume of a gas also increases, as long as the pressure remains constant. This is exactly what Charles' law explains. Now, let's connect this idea to something we encounter in our everyday lives. Let me ask you a question. Who among you uses insect spray, hairspray, aerosol spray, or similar products at home? Many of these products contain gases stored inside a sealed container. When the temperature around the container changes, the gas inside also responds to that change. Because gases are sensitive to temperature, heating or cooling can affect how they expand or behave inside the container. According to Charles' law, when the temperature of a gas increases, its volume expands if the container allows it. However, in a sealed pressurized can, the gas cannot expand, so instead, the pressure inside increases significantly. This is one of the reasons why aerosol containers often include warnings such as do not expose to high temperatures, never burn or expose a pressurized can to extreme heat. Instead, dispose of it properly following local waste management guidelines. Why is this important? These containers are sealed, which means the volume of the gas inside stays constant. When the temperature increases, the gas particles move faster and collide with the walls of the container more often. This causes the pressure inside the container to increase. This relationship between temperature and pressure is explained by Gay-Lussac's law. Gay-Lussac's law states that when the volume of gas remains constant, the pressure of a gas is directly proportional to its absolute temperature. The formula for Gay-Lussac's law is P sub 1 over T sub 1 equals P sub 2 over T sub 2, where P sub 1 is the initial pressure, T sub 1 is the initial temperature, P sub 2 is the final pressure, and T sub 2 is equal to the final temperature. Remember that temperature must always be converted to Kelvin when solving gas law problems. Now, let's apply this formula to a sample problem. A sealed LPG tank is stored in a kitchen at 298 Kelvin with an internal pressure of 2.4 atmospheres. A fire breaks out, raising the temperature to 673 Kelvin. What will be the new pressure inside the LPG tank? This problem follows Gay-Lussac's law since the volume is constant and temperature changes. Given P sub 1 is equal to 2.46 atm, T sub 1 is equal to 298 Kelvin, and T sub 2 is equal to 673 Kelvin. We are asked to look for the final pressure. We use the Gay-Lussac's law, which is P sub 1 over T sub 1 equals P sub 2 over T sub 2. Next is to derive the formula for P sub 2. P sub 2 is equal to P sub 1 times T sub 2 all over T sub 1. Substituting the values, we get 2.46 atmospheres times 673 Kelvin all over 298 Kelvin. P sub 2 is equal to 5.56 atmospheres. The new pressure inside the LPG tank is approximately 5.56 atmospheres. As the temperature increases, the pressure inside the steel tank also increases, which follows Gay-Lussac's law. This is why LPG tanks should never be exposed to high temperatures or fire. A can of insect spray has an internal pressure of 2.96 atmospheres when stored in a cool room at 291 Kelvin. If the can is left outside under the hot sun and the temperature rises to 223 Kelvin, what will be the new pressure inside the can? This problem still follows Gay-Lussac's law since the volume remains constant and only temperature and pressure change. Given P sub 1 equals 2.96 atmosphere, T sub 1 equals 291 Kelvin, and T sub 2 equals 323 Kelvin. We are asked to look for the P sub 2 or the final pressure. We still use the Gay-Lussac's law, which is P sub 1 over T sub 1 equals P sub 2 over T sub 2. Next is to derive the formula for P sub 2. We'll use the equation P sub 2 equals P sub 1 times T sub 2 over T sub 1. By substituting the values, we can see that the new pressure inside the insect spray can is approximately 3.29 atmospheres. Before we move on, let's briefly review the three gas laws we have discussed. First, we have the Boyle's law, which states that when the temperature is constant, the pressure of a gas is inversely proportional to its volume. This means that when the pressure increases, volume decreases, and when the pressure decreases, volume increases. Next, we discussed Charles's law, which states that when the pressure is constant, the volume of a gas is directly proportional to its absolute temperature. In other words, when temperature increases, the volume of the gas also increases. We also learned about the Gay-Lussac's law. This law explains that when volume is constant, the pressure of a gas is directly proportional to its absolute temperature. This means that as the temperature increases, pressure also increases. Now, you may notice that these three laws describe relationships among pressure, volume, and temperature, but each one keeps one variable constant. But what if all three variables change at the same time? To describe the situation, we use the combined gas law. The combined gas law summarizes the other gas laws by combining the relationships between pressure, volume, and temperature into one single equation. It brings together the ideas from Boyle's law, Charles's law, and Gay-Lussac's law. Instead of studying how only two variables change at a time, the combined gas law shows how pressure, volume, and temperature of a gas change together when the amount of gas stays constant. This allows us to predict how a gas will behave when any of these three variables change simultaneously. In short, the combined gas law summarizes and unifies the relationship described by the individual gas laws into one equation, making it easier to understand and calculate the behavior of gases under different conditions. The formula for combined gas law is P sub 1 V sub 1 divided by T sub 1 is equal to P sub 2 times V sub 2 divided by T sub 2. Using this equation, we can solve problems where pressure, volume, and temperature all change. Let us now apply the concept of combined gas law to some problems to see how these variables work together. A scuba diver has a tank filled with 2.5 liters of gas at a pressure of 200 atmosphere and a temperature of 300 Kelvin. As the diver ascends, the gas expands, and the final conditions are 3.5 liters and 320 Kelvin. What is the new pressure inside the tank? This problem involves changes in pressure, volume, and temperature, so we use the combined gas law. First is to identify all the given values. P sub 1 is equal to 200 atmosphere. V sub 1 is equal to 2.5 liters. T sub 1 is equal to 300 Kelvin. T sub 2 is 3.5 liters. T sub 2 is 320 Kelvin. We are looking for the P sub 2. We derive the formula for P sub 2. P sub 1 times V sub 1 over T sub 1 equals P sub 2 times V sub 2 over T sub 2. We first multiply both sides of the equation by T sub 2 and divide both sides by V sub 2. So we can get the equation P sub 2 equals P sub 1 V sub 1 times T sub 2 all over T sub 1 times V sub 2. By substituting the values, we now have P sub 2 equals 200 atmospheres times 2.5 liters times 320 Kelvin all over 300 Kelvin times 3.5 liters. The new pressure inside the tank is approximately 152 atmospheres. As the diver ascends, the gas expands and the temperature rises slightly, but because of the pressure, volume, and temperature are all intact, we must use combined gas law to calculate the final pressure accurately. Finally, a weather balloon is released at sea level where the pressure is 1 atmosphere. The volume is 5 liters and the temperature is 290 Kelvin. As it rises, the pressure drops to 0.5 atmosphere and the temperature decreases to 250 Kelvin. What will be the new volume of the balloon? Given initial pressure is 1 atmosphere, initial volume is 5.0 liters, initial temperature is equal to 290 Kelvin, the final pressure is 0.5 atmospheres, the final temperature is equal to 250 Kelvin. We are asked to find the final volume of the balloon. For the equation, start from the combined gas law, which is P sub 1 times V sub 1 divided by T sub 1 equals P sub 2 times V sub 2 divided by T sub 2. Again, we multiply both sides of the equation by T sub 2, then divide both sides by P sub 2. We will use V sub 2 equals P sub 1 times V sub 1 times T sub 2 all over T sub 1 times P sub 2 as our final formula. Then, we substitute the given values. V sub 2 is equal to 1 atmosphere times 5 liters times 250 Kelvin all over 290 Kelvin times 0.5 atmosphere. The new volume of the weather balloon is approximately 8.62 liters. As the balloon rises, pressure decreases and temperature also decreases, but the effect of decreasing pressure dominates, so the balloon expands. The combined gas law allows us to calculate the new volume accurately when the 3 variables are changed. Just like the weather balloon, gases respond to changes in pressure, volume, and temperature. But gas laws aren't just for experiments. They are also critical in real-world engineering. Take airbags in cars, for example. In a crash, airbags must inflate within milliseconds to protect passengers. A chemical reaction inside the airbag system produces hot nitrogen gas, which expands rapidly and fills the bag. If the temperature of the gas gets too high, the pressure could become dangerous. The airbag must burst. This is where the combined gas law comes into play. It explains how pressure, temperature, and volume interact to control inflation. By carefully increasing the volume of the bag, engineers prevent dangerously high pressures. Proper airbag design balances pressure, temperature, and expansion to keep passengers safe. This is also a perfect example of how science and gas laws save lives in real-world applications. Before we finish, let's do a quick target check. Think about everything we've learned today. Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. Can you now investigate and explain how volume, pressure, and temperature are connected in different situations? Take a moment to reflect on the examples we discussed, from balloons and hot air balloons to insect sprays and airbags, and see how these laws apply in real life. Understanding these relationships is not just theory, it's awesome science. If you like more science videos, make sure to subscribe to this channel. Thank you, and always remember that you are all awesome.